Okay, so the next talk will be given by Isobel Hook about foremost Time Domain Extragalactic Survey.
Thank you very much, and thank you to the organisers for the invitation to talk about this. So I'm going to talk mostly about the Time Domain Extragalactic Survey, TiDES, which is one of many surveys that are going to run on Foremost. This is the only slide I've got where I show all the institutes involved in Foremost, and obviously that is absolutely essential for the operation of TiDES to be able to go ahead. So this talk is on behalf of the TiDES team, but I particularly want to thank Chris Frohmeyer, who's provided quite a lot of the input for this. So this is just two overlapping subsets of the TiDES team. Those are the best photos I could find, but just to give you an idea, and I just like these photos because it shows the sun shining in both Lancaster and Dublin, which I don't know how often that happens, but there you go. So the very brief overview of Foremost. So the PI is Roloff de Jong, and this is an optical spectrograph that's going to go on the 4-meter Vista telescope. It has a 4 square degree field of view, and the heart of it is this positioner, which now I'm trying to, there's a little movie here, which I need to start. And there we go. Let me start. Okay. Yeah. Oh, it's got sound. Wow. So the ESO positioner there is moving. It's the set of these spines that can be moved to align with your targets. And there are 2,400 of them in this hexagonal pattern on the sky. So about 2/3 of those feed low resolution spectrographs, and 1/3 of them go to high resolution spectrographs. And TiDES is exclusively using the low resolution fibers. So Foremost is going to survey basically the whole southern sky over about 5 years. And it has, as I mentioned, many surveys, so that depending how you count, there are 18 participating surveys, and they cover extragalactic and galactic targets. And the whole thing is now expected to start around the middle of 2025 for a 5-year survey. And that, there's still some uncertainty in that schedule, but there will be some science going on before in the survey performance verification phase. So there will be some start, some initial results, and at least being able to test the performance thoroughly before that date. And I should perhaps mention the instrument is basically complete now. It's being built in Potsdam. It's undergoing some final testing and will be shipped later this year. So that's all I was going to say about Foremost. I want to get on to TiDES mostly. So I'm currently the PI, but this is a rotating position. And I'd like to stop that sound now. I don't know if that's going to be possible. I'm going to... There we go. Okay. So the basic principle is that everywhere that Foremost looks in the sky during this survey, there will be live transients that LSST has discovered within a few days before that, because LSST is going to be continuously surveying the sky. So the idea is that TiDES is going to piggyback on these other surveys that Foremost is doing and just allocate a few fibers per field to live transients and ones that are still bright, but also the host galaxies of transients that have faded away. And the goals of all this is we want to get spectra of as many live transients as we can. We want to get redshifts of the host galaxies. And there are also programs to do AGN reverberation mapping and follow-up of strong lenses. And I'm not going to talk about those at all, but they both come under TiDES because of the time domain aspect of them. So the allocation of time for TiDES is about 250,000 fiber hours allocated over the 5 years. And we think that's plenty to do what we want to do. And we're now designing the survey. So most of what I'm going to talk about is, sort of how the survey is going to work and what we expect to get out of it. So I've just got this overlap diagram. This is one of the older survey plans for LSST, just showing the sky coverage of where the LSST survey will be. And Foremost will cover this sort of purple area. Again, not the most up-to-date plan, but you get the general idea that there's a large overlap area of about 13,000 square degrees. So this is ideal really for following up LSST targets. But the real key is the time domain aspect. And this is a very nice animation that Chris Frohmeyer has made. I think you may have seen this in Kate Maguire's talk. So what this is showing is where Foremost plans to observe as time goes on. the important thing is when LSST is running at the same time, and it may just take a minute to get to that point, and I can't control this from here. I'm just going to have to let it wait. So in a minute, you'll see where LSST is observing. And actually, this does make one of the key points. The timing of the two surveys starting is really important. Here we go. So this is now showing where how recently LSST looked at a field. So you can see the color bar on the right is showing the time, and where foremost is pointing. So you get an idea from this that as LSST is observing the sky, foremost is going to be looking kind of randomly at the same general area. And as time goes on over 5 years, we'll get a large sample of transients, but obviously we're going to miss a lot as well. And this is all dependent on the survey strategy as well. So I just want to summarize how we're going to select the targets. So what we're aiming for with the live component of TiDES is sort of basically most types of transients, but we won't really know what they are before we observe them. But we're aiming for type 1a supernovae, core collapse supernovae, kilonovae, tidal disruption events, superluminous supernovae, and all sorts of interesting things that we don't know are out there. So our primary selection criteria are just a magnitude limit of 22.5, which is quite bright actually, and I'll come back to that later on the difference image. We're not planning any color selection in our primary sample, and then there are some criteria just to make sure that they're real targets. So we have a 5 sigma detection requirement on more than one epoch, and a detection in more than one band, or 3 bands actually. That's color bands in LSST. And then, so that's the primary sample. It's basically this flux limited sample, but we will also be having some fainter samples or other specially selected samples that we can add on and try to get those as much as we can as well. And then for the host sample, here we're going after redshifts of old supernova host galaxies. The limit will just be set by what foremost can do, which will be around 22nd magnitude. But in the deep fields where foremost keeps going back and we can stack the images, the spectra will be able to get to about 24th magnitude, we think. And this is just giving a sort of idea of what the data quality will be like. So on the left are just some simulated LSST light curves following that pattern. So this was all done by Chris Frohmeyer and Maria Vincenzi. So there's various redshifts shown there. And on the right are the expected quality of the spectra from foremost, assuming 1 hour exposure times, which may actually not be the case. They may be 40 minutes, but it won't change a huge amount. So you can see examples at different magnitudes there. So when you put this whole time domain simulation together and work out where LSST is pointing, where foremost is pointing, and you put those selection criteria in, this is what you get out for the number redshift distribution of different types of transients. And so there's a lot on here. There are lots of different types of transients, and there are 2 sets of lines for each type. There's a kind of best estimate and an optimistic estimate, depending on the survey schedules. But you can see from this, the type 1a supernovae, they're the red histogram there. They dominate, particularly at the lower redshifts. And so they go out to about redshift 0.5-ish. So we expect something like 35,000 live transients over that 5 years, and we'll be able to use these for all sorts of things, mainly classification, but some transient physics, maybe triggering other observations on other telescopes, and importantly, training. This will be a very important training sample for machine learning algorithms for photometric classification. For all the objects that we didn't get spectra of, we'll be able to use this as a training sample to classify those. And of course, selecting the type 1a supernovae for cosmology. So in my remaining time, I want to go through a few things that we're working on now in preparation, and most of this is kind of simulating what we think we're going to get. I won't have time to go through all of this, but I wanted to just highlight at the top some work that my student John Carrick did to demonstrate that you can use TiDES data as a training sample for photometric classifiers, even though there is this magnitude limit. You can actually use it to classify objects fainter than that, as if you can train your algorithm with machine learning and data augmentation, and maybe supplement with a few fainter objects, it actually works very well. But what I'm going to show is some simulations about the cosmology that we get from type 1a supernovae, and some work on spectral classification and photometric classification that we've been doing in Lancaster. So first, the cosmology that we expect from TiDES. So this is the end point of Chris Fromeyer and Maria Vincenzi's simulations, which go all the way from end to end, from the LSST light curves through the foremost observations, through a sort of simulated classifier to pick out the type 1As, and you end up with a Hubble diagram, which is what we've got on the left here, showing the distance modulus against redshift. So you can see the live supernovae, the ones with spectral classification, are shown in red there. The blue ones are objects that have been photometrically classified but have a redshift from TiDES, and that allows you to go a little bit higher in redshift. And we've also got the AGN from the reverberation mapping campaign there. So those are shown in green, going out to higher redshift. And we think that with all those things together, we should be able to get something like a 2% uncertainty on the equation of state parameter for dark energy, the W parameter, which would be a very nice result. I think I'll skip the details of that. So I want to go on to how we're going to, well, what we can do with classifying the spectra. So I've called this "What was that spectrum?" So here I'm talking about the end point of this, where the data's come off the foremost instrument, and we need to classify the spectra into what type of transients they are. And here we need to, well, we've actually committed to provide the classification and redshift within 24 hours and provide that back to the community. So the question is, which of these spectral classifications tools should we use? There are plenty in the literature, and we want to find out what sort of performance we can expect and how well they work with TiDES quality spectra, and can they deal with the host galaxy contamination. So we've been doing some simulations to produce host galaxy contaminated spectra. So there's an example on the right here, produced by my student Andrew Milligan. And so that shows both the combination of a type 1A supernova spectrum and a host galaxy blended at roughly equal fractions. And that particular one is at redshift 0.3. So that's the sort of quality we're going to get in the middle of our redshift range. So what Andrew has done is worked out how much light from the supernova will go down the foremost fiber, just based on the seeing, but also how much light from the host galaxy is going to go down the fiber. So that's the middle plot there, assuming certain parameters about the host galaxy profile, and then put those two together, put the whole thing through the foremost exposure time calculator, and you end up with the blended spectrum on the right. And he's going to do this, or he has done it now, for the whole simulation that I showed you that Chris Fromeyer made. So we've got, you know, many, many thousands of these objects now, and we can do tests to see how well we can classify them. So this is just preliminary work, and I'm not really going to go through it, but he's looking at the DASH, which is a machine learning classifier, next generation SuperFit, and SNID, which I'm sure many of you are familiar with, all of those. And testing, they perform relatively differently in different regimes. So in this particular case, he was looking at how much exposure time matters, but we can also do things like test, are there different redshift ranges where these classifiers work better? Maybe when there's more host contamination, one works better than the other. So that's the sort of thing we're trying to do now so that we're ready to go. And then the second example I wanted to talk about is about the host galaxies. So this is some work that my other student, Jamie Dumain, has just done. He's just finished his thesis and defended it. So this is an idea to see how well we can determine the physical properties of host galaxies from the TiDES spectra. So what he's done is taken an example galaxy spectrum, and it's actually a known one. It's a model galaxy spectrum where we know its stellar mass and various parameters like star formation rate, scaled it in redshift and in brightness, calculated from that what the LSST photometry for that galaxy should look like. So those are the red points on these graphs at the bottom, and also simulated the foremost spectrum. So that's actually that's not shown on here. And then adding the right noise with the foremost exposure time calculator, we then fit both the photometry and the spectrum using an SED fitting code to get out things like redshift, mass. Actually, in this case, redshift was fixed, but mass, stellar star formation rate, age, various other parameters that the code spits out. And the results from that show that obviously adding the spectral information improves the uncertainties on these parameters. So there's two graphs here. The top one is about stellar mass, which just scales linearly with the brightness of the object in this SED fitting code. But the important thing to look at is the size of the error bars. So the photometry, LSST photometry, gives you the orange error bars, But when you add the spectra, you get the smaller error bars shown in sort of cyan color. And so for stellar mass, you can see it improves basically at all magnitudes and actually at all redshifts as well. And age as well, when the age parameter comes out very much improved as well when you add spectra. So this is very encouraging. And so what he's done really is quantified how much improvement this is, and I'm going to show how that's useful in a minute. What we did find, though, is that it doesn't actually help all that much in the mass step for cosmology, for supernova 1A cosmology. It turns out to be negligible, but it does seem to help when you come to try and classify transients. So I'm going to come to that. That's the last thing I want to talk about. What was that light curve? So what we're trying to show here is how much this extra host galaxy information that you could get from TiDES is going to help classify supernovae photometrically. So imagine now that you haven't got a spectrum of the supernova, you don't know its spectral classification, you've got a light curve from LSST, but we do have the redshift of the host galaxy and some information of the physical properties of the host galaxy. And so what we were hoping that would happen is, because rates of different types of supernovae depend on the host galaxy type, we're hoping that that extra host galaxy information will help us classify the light curves. So what we did here was use a machine learning approach to do the photometric classification, and we've used Supernova by Anais Muller, the code, which is a machine learning code. And what it does is try to classify a whole light curve, or at least that's the mode we're using it. Not trying to do real-time classification, but the full light curves. So we're using the LSST simulated light curves that I showed you earlier. So we've got the LSST light curves simulated, and then we add in, which I should mention in those those simulations, that Chris included some correlations between various supernova rates and host galaxy properties. So that's what we're relying on helping. So what we did then is add into supernova extra information. So we give the host galaxy properties redshift, stellar mass, and star formation rate to the machine learning algorithm, and see if that helps it train. We train it on that and see if that helps it classify the light curves of another test set of data. And we find it does. So these are the results. So what we're seeing here is that the metric we're using is the precision of the classifier, which is 1 minus the contamination rate. So that's along the x-axis, and then on the sort of going up is various additions to the data set that we're using. So the bottom one here is just giving this supernova machine learning algorithm only the light curves. And you can see already it's doing very well. It's got a precision of over 96%. But you can actually do better. So if you add in photometric redshifts, again, just from the LSST simulations, it does a little bit better. So that's the pink data point. When you add in the spectroscopic redshift from TiDES, you do quite a bit better. So that's the blue. So this is all in the spirit of what we heard yesterday from Matthew Graham about trying to, get from 99% to 99.999. We really want to do as well as we can with these classifications. So obviously the spectroscopic redshifts help. The next point up in yellow is what would happen if we go back to just photometric information, but now we've got not just the light curves and the photometric redshifts, but photometric host properties. So that's like the big orange error bars on Jamie's plots. So you can estimate these properties, but it's pretty poor. And actually it makes the machine learning algorithm, it performs worse than if you don't add that host galaxy information. We think that's just because the uncertainties are so large, it's just sort of confusing it. So then we go one more step up. The green there is if you have a light curve, a spectroscopic redshift from TiDES, and a spectroscopic host properties like star formation rate and mass, and then you do even better than you do with just the redshift. And then finally, the point at the top is if you had no uncertainties at all. So what you can see from that is that it's not that the TiDES data is essentially doing as well as the perfect host galaxy properties. So it's not the TiDES data quality that's limiting this. It's the whole, the algorithm for using host galaxy properties in the first place. Okay, very last thing I want to say is a bit of a data flow thing. So we've seen lots of these types of diagrams. This is put together by Chris Frohmeyer as well, and it's just showing how we go from LSST producing these alerts. Within about 60 seconds, we should receive those alerts through the brokers should receive them. We then apply our TiDES selection function and send information to Foremost, and we're hoping to be able to update our observing blocks on, hopefully a sort of nightly timescale. I think the requirement is about 3 nights, but we think we can probably get this system working fairly rapidly. So that at that point, the objects will be in the foremost queue, and foremost will observe them if they happen to be in the right field of view. We'll get a transient spectrum. And as I said, we hope to release the classification in redshift within about 24 hours. The point I wanted to make here is that it is possible to get other streams of data into this process. So as I mentioned, this is not a TOO system to react to single objects, but if you've got a sort of a survey that's producing objects in a well-defined way, they could potentially go into this process as long as that we can add a flag to it. It should be possible to get other streams into this information, into this process. Okay, that's my last slide. So just a summary then, we're hoping TiDES will produce about 35,000 live transient spectra over 5 years, which are useful for all sorts of things, classifying objects, physics of transients, triggering other observations, and the Type 1a supernova cosmology. And we'll also get about 50,000 host galaxy spectra for supernova cosmology. And I will stop there. Thank you.